Sum principle is kind of the most obvious counting principle you can think of, and it's kind of deceptive because by itself, but then I think it's going to think about it, a bunch of questions that gradually grow more complicated and interesting. And also, it often pops up as a step in conjunction with other principles that you can use to solve really hard problems. So let's imagine that we have two people. We're always going to start out with our two people because those are the two main characters of every math drama. Have you all seen Alice and Bob before? Well, Alice and Bob are like main characters in lots of math stories. So let's say Alice has $5,000, Bob has $2. And the question is, how much money do they have all together? 5,002? Do you agree? Pretty straightforward, right? You can just combine them. Bob would probably be very happy about that arrangement. Let's look at the next question. If Alice has 17 friends and Bob has 15 friends, how many friends do they have combined? The temptation is 32, but it might be a trap. Why? Some of those friends might be the same friends. So it's a different situation. And it could be 32. That's the largest it could be. What's the smallest it could be? It turns out these questions get complicated, even though they seem simple. And part of the deceptive simplicity is due to the happy looking people in the pictures. You don't know what it could be. It could be that it has 17 friends and Bob has their 17 friends and that these two sets are completely disjoint. Or it could be that Bob doesn't know anyone that Alice doesn't know. In that case, we would have like two people out here who are not Bob's friends and then Bob would have the other 15. Or it could be anything in between. This information that we have could be anything between 17 and 32. It couldn't be larger than 32 and it couldn't be smaller. So we're going to now discuss notation that we could use so we can talk about these two different types of problems. In this one, there is no overlap. Alice and Bob, we don't think have a joint bank account. So here in question one, there's no overlap. And here in question two, we don't know how much overlap there is. There is potential overlap. So these are two different situations. But we want to take these simple looking questions and give them some mathematical rigor and notation so we can look at definitions of symbols that knowledge. I want to explicitly tell you everything that I expect you to know. If X is a set and I put these bars around X, what I'm expressing here is the number of elements in X, also called the cardinality. People sometimes say size, but we're not going to use that term because size has a different meaning in discrete structure. So we're going to always call this cardinality. So for instance, if we have Q is 1, 2, 5, we would say that the cardinality of Q is 3. People are sometimes tempted to call this absolute value, and it kind of is, because if you think about it, absolute value of a number telling you the size of magnitude. This is also the symbol that's used for magnitude of a vector. So this is a mathematical symbol that always means the magnitude of whatever you're looking at. And the magnitude of a set, it makes sense to say, is the number of elements that are in it. And if A and B are sets, then when you look at A union B, this is going to be a new set. It contains all elements of A, elements of B, and anything that's in both. I always think about union as a cup, like it's an open cup and you're pouring everything you can into it. It'll take it all. It's not restricting it. That notation, I could ask you if I have A is 1, 2, 3, 4 and B is 7, 9, 11, 12, 15. What's A union B? You all agree? Hey, you just take everything from this set and this set and write it out as a set. You've seen that idea before, right? I'm going to go ahead and tell you some of the traps that I could potentially pull on you in future questions, is people forget what this means. So this is a set. When I put the absolute value bars looking around it, it's a number. The cardinality of A union B, what would that be? 9? Because there are 1, 2, 3, 4, 5, 6, 7, 8, 9 things together. Be careful if you're looking for the bars or not. The bars are telling you to look for a number. If there are no bars, it's going to be a set. So in this case, the size of A was 4, and the size of B, the cardinality of B was 5. And when you took the union, you just added those together. It's going to lead us to our first big principle here, which is the sum principle. So if A and B are disjoint finite set, then the cardinality of A union B is equal to the cardinality of A plus the cardinality of